In this paper, we made three main contributions. First, a constraint slam formulation. Second, a metric to predict objective function change in the incremental scheme. Third, a bench incremental design, which is robust against local minima and outliers. First, let us consider the cycles of the graph. There are three cycles in this graph. The mathematical representations of these cycles are given here. Usually, we want to consider a set of independent cycles named a cycle basis. Since a cycle is a composition of edges, it is natural to ask a question like, what if we take the edges as variables to be estimated? If we take edges as variables to be estimated, we get a constraint slam formulation. The constraints are a cycle basis of the graph. The constraint slam formulation is a nonlinear optimization problem with equality constraints, which can be easily solved by sequential quadratic programming. Under the constraint slam formulation, an incremental slam algorithm can be regarded as a sequence of subproblems, where each subproblem can be uniquely identified by a constraint saint. The key of an incremental slam algorithm is to design the constraint saint for each subproblem. An incremental algorithm is empirically observed to be robust against local minima. An explanation of this phenomenon is that the solution of the previous subproblem is more likely to lie within the basin of convergence of the next subproblem. Based on this insight, we can further enhance the robustness of an incremental algorithm by ensuring the closeness of solutions between subproblems. However, the closeness of the solution cannot be measured directly unless you solve the problem. So to benchmark the closeness of solutions, we use the closeness of the objective function. The problem is, how can we measure the closeness of the objective function without solving the problem? It comes to our second contribution, which is a metric to predict the objective function change without solving the problem. Finally, we propose a bench incremental slam algorithm using the predict objective function change to select measurement. According to the least objective function change to increase robustness against the local minima, and the chi-square difference test to increase robustness against outliers. The experiments validate the robustness of our algorithm. This concludes the short introduction of our work. Thank you.